Today's topic is mass wasting. Mass wasting means landslides. And the reason why it's called mass wasting is because these are large failures. That's another way to, like, if you were to interpret mass wasting, think of it as large failure. In the textbook, this is chapter 10, and in general, the non-technical term for all of this is landslide, but you're going to see today that there's different processes and different types that we can categorize in certain ways. So mass wasting is our main topic, and before we get started, you could just open a new tab, type into YouTube search mass wasting event, type in landslide, type in debris avalanche, and just watch some of these events unfold. It'll be awe-inspiring, it'll be interesting, it could be sad, and then go ahead and do it again when we're done with this video and look at it now from a lens of what you've learned. The reasons why we study mass wasting, I think there's twofold answers to that question. So why are we studying them? The first is going to be, this is a major way that landscapes evolve. As we go from mountains brought up by plate tectonics to flat lands produced by erosion, somewhere in between the two of those, there's going to be mass wasting events, failures of steep topography, putting material down slope. So it's landscape evolution is a major scientific reason why we should study mass wasting events. It's a natural major process. And then the human side of why we should study mass wasting is it is a very significant hazard to life and infrastructure. Life plus infrastructure. Sometimes events don't kill anyone, but they cause millions to billions of dollars of damage, and sometimes they do both. On average in the United States, about 25 people die each year due to a mass wasting event killing them, and it's around 1.5 billion in terms of infrastructure damage every single year. And this is just in the USA, where we have a lot of wealth, a lot of scientific resources, and a lot of really amazing infrastructure to make this not happen. And this year alone, which is 2024, we are much higher than both of those numbers. So, the science of it. There's going to be 4 controls to mass wasting events. We'll walk through them, 1, 2, 3, 4. Number 1 is going to be angle of repose. And when we talk about angle of repose, I also want you to be thinking about a force balance. And we'll do sketches for both of these concepts. And if you want more background, go to chapter 10, go to Wikipedia. Of course, there's much more that you can learn about each of these things. Angle of repose is the steepness with which loose particles will set. And so here's a picture. It's a pile of sand, and there's a conveyor belt bringing sand and dropping sand down onto this pile. And generally speaking, the angle of that loose sediment for loose sand is going to be 35 degrees. And depending on the size and angularity of your particles, the angle of repose for loose disaggregated sediments can be somewhere between 35 to 45 degrees. If you oversteepen beyond that number, you will have a little bit of a landslide, runs downhill. Now, another way to think about this as a control is this concept of a force balance. And so for a force balance, here is a block sitting on some angled land. And we can break down the forces that are acting upon this block. In general, there's going to be 2 main forces. One is gravity, of course, which is pulling this block down. So Fg is the force of gravity. And gravity is going to be pulling in 2 different ways. It's going to be pulling normal to the surface, and so this we're going to call the normal force, Fn, and it's also going to be pulling down, directly downhill, and this is our downslope force. This is Fd. There is one other force that we need to consider, and that is the cohesion between the block and the land, and that we're going to call a resistance force, Fr, and we can think of that as friction. And so landslides, mass wasting occurs when Fd wins. And there's going to be certain situations where Fd wins, okay, when that downslope force is able to overcome the gravitation, the normal force and the resistance frictional force. And it's going to win in 2 instances, one when the terrain is steeper, and 2 when there is less friction and less friction tends to be more water. All right, and that's going to take us into the next of the controls. So number 2 is water content. And water content presents to us a duality. Water can do 2 different things. Water can either strengthen a slope or it can weaken a slope. And so, in fact, let's just say that when there's high water contact, what's another way to say that? That's like saturated or oversaturated. This means high water content. And what high water content will do is it will act as an interstitial lubricant. Basically, it increases the pressure between the pores and the porosity, and all the grains start to detach from one another. And when they detach from one another, everything is weak and landslides can occur. So interstitial lubricant. If we were to have a picture of this, we would have these grains of sand, and when there's a ton of water between those grains of sand, basically there's pressure that's pushing those grains apart, and as you push apart the grains, what a terrible drawing, you can get a landslide. Now the duality here is that when there is a low amount of water content, you can actually pack the sand and you can build a sandcastle. That's because cohesion can be produced by surface tension. And so this is when we are, we could just say less saturated, a little bit drier. It's not fully dry, but less saturated. All right, so water can be both good and bad, and in our biggest events, the most devastating natural disasters, it tends to be in big rainfall events when water content oversaturates the ground. All right, so then number 3 in this is going to be our slope materials. The type of landscape and whatever the mountain is made of is going to matter as well. There are weak rocks and there are strong rocks. And so a big player here is when your mountainside is made up of a weak rock. What is a weak rock? It's anything that has been weathered and altered. That's going to be your weakest type of rock. There's another really weak type of rock. It's a sedimentary rock called a shale. And so when mountains are made of either of those 2 things, we have a higher likelihood of failure. A good example of this might be a volcano. And you know, volcanoes are hot and there's a lot of alteration that's going on. And so the sides of a volcano could be very weak because they've been altered, which could make this side of the mountain want to slide down. The other aspect of a slope that matters is what we call structural orientation. And I think a drawing here will help more than me just talking. So if we have, here's our mountainside, and the actual rock units are oriented this way, this is a very weak environment. Now let me show you the direct opposite. Here's our mountainside, and now here's how the rocks are in the subsurface. This is a very strong environment, because in this orientation, the bedding planes in the rocks actually parallel the topography. This is called a bedding parallel structure. And when you have a bedding parallel structure, the bedding planes actually act as like slips and slides that allow mass wasting events to occur. You can imagine it that like this right here detaches, and if that detaches, all the material above it can just slide right down. But you can't draw something similar on this side because the bedding just kind of acts as little dams and steps that block it from sloping away. Now our 4th trigger is called an earthquake. And an earthquake is external. I guess water is external as well, but the earthquake is just a shake, and it can just act as an external trigger. And sometimes our largest avalanches and landslides occur in response to earthquakes, which weaken the terrain. Now to finish off, I want to go into one last category here, and this is going to be how do we classify. All right, maybe we could title this classification. And we classify different types of mass wasting events based on 3 things. We do it based on their coherency and how fast they move, their speed. And then finally, we do it based on their water saturation. And there's a whole list of these different terms. I'm only going to introduce a few of them to you. And what I'd like you to do is graph them, something like this, where on one axis we have water saturation, where we go from dry to wet. And on the other axis, we could categorize it based on speed, from fast to slow. And I'll try to put these on here. And when we think about saturation, I think you could almost think about prediction, because we know when rain falls. And when there's a lot of rain, then we know that we can predict the amount of saturation. Speed, on the other hand, maybe is a better proxy for hazard. If an event moves very slowly, it's not as dangerous. We could even get out of the way. Whereas if an event occurs very quickly, it could be a very huge hazard that can kill a lot of people. So I'm going to walk you through a handful of different, there's 5 here, just 5 different types of mass wasting events. The first is called creep, and we're going to include creep because it is very slow. It tends to be, here we go, creep. Creep is very slow. It's occurring at something like centimeters per year, and it happens on the wet, dry, freeze-thaw cycle. So if here is our mountainside, and we freeze the mountainside, and then we thaw the mountainside, and we freeze the mountainside and thaw the mountainside, each time between those cycles, the soil might slip just a little bit downhill. And it goes so slowly, in fact, that one of the only records of it is like trees are bent as they fight towards the sun, but the amount of motion is just on the order of a few centimeters. All right, so that is dry and very slow. I could insert a picture of what creep looks like. Here's a good example of it. Now in this case, we don't have trees, but we see a fence that's been knocked over. They didn't build the fence at this angle. It's been slowly shifted downhill as the soil is slowly creeping its way with every rainfall or dry period, allowing just a little bit of grain by grain motion downhill. All right, number 2 is a slump. Now, one thing I should have said under creep is that it is coherent. The particles aren't breaking apart. Instead, you get like the whole hillside is moving together as one. That's what I mean by coherent. And a slump is coherent as well. A slump might be occurring at a few kilometers per hour. Probably, it might be fast enough for you to run away from, or at least drive away from. Okay, a few kilometers an hour is the speed, and it's a spoon-shaped landslide. So here would be an example of a drawing of a slump where here's a block that is detached and it's moved its way slightly downhill. The scale here, here's a couple trees to show you what the scale of this might be. And the spoon shape, here's the spoon. It's these spoon-shaped scoops that scar the landscape. The key here is that it's coherent and the whole block moves together. Number 3 is going to be a rock slide. And with a rock slide, what we have is it tends to be in cliff mountain areas, and we can have some kind of block detach and move downhill. It starts off coherent, and then by impacts, we might get a bunch of rubble talus sitting at the bottom. We could say something like, let's just say a detached bedrock. We can add both of these to our graph. If creep is very slow, slump is a little faster. It also tends to occur when the ground gets wet, and then rock slides very fast, but also very dry. Rock slide. All right. 2 left that I'd like to share with you. And these are kind of they're kind of related with one another. 4, we'll do it like this. 4 and 5, we'll do a cutoff between, and we'll put the word H2O between these, because this one is a little more dry and this one is a little more wet. And the key for both number 4 and 5 is that these are also unconsolidated. Once the landslide occurs, all right, the failure occurs, the mass wasting event occurs, all the particles break apart from one another, and so they become unconsolidated. This is true for both numbers 4 and 5. So number 4 is going to be a debris avalanche, and number 5 is a mud flow. Sometimes mud flow is also called debris flow. It depends on how big the particles are inside of it. And a mud flow is rich in water. So we could say this is a water-rich slurry. It's like wet concrete flowing over the ground. It's moving at 1 to 100 kilometers per hour. These things can really move, and they can be incredibly dangerous. And the debris avalanche, this is where there's more rock than water. I'm not saying there's no water, but there's more rock than water, whereas the mud flow, we could say, is water greater than the amount of rock. So we can add both of these to our diagram. The rock slide is pretty similar to a debris avalanche, just has more water in the debris avalanche. And the debris avalanche is kind of similar to a mud flow, but the mud flow has more water, right? They're all fast, they're all very hazardous. I'm drawing these arrows in to just kind of show you that it's possible for a slump to eventually give way and turn into a mud flow, or for a slump to turn into a debris avalanche to turn into a mud flow. You can imagine a lot of ice in a debris avalanche that starts to melt, and so it turns into this mud flow. Let me just show you a couple pictures here, and then we'll get out of here. Here's an example from the state of Washington. Now I'm showing you pictures where people died in these different events. There was a community in the state of Washington sitting here at the bend of this river, and what's amazing, look at this, they built their community right by this scar that's spoon-shaped. That's an ancient slump that occurred. Well, in 2014, that slump gave way again and sent this landslide down across the community. Let me show you a picture of another disaster. This happened in the country of Venezuela. And first thing I want you to see in the background, look at all these. These are places where small mud flows occurred on the steep slopes because of a significant rainfall event. Everywhere you look in the mountains, there's these scars. Well, they fed together in these valleys and created a significant, what would be a debris flow. Very water rich, but full of just debris, not just mud, huge boulders, which then ended up burying the landscape and people.